The B-17's deadliest secret wasn't German fighters. It wasn't the blistering cold at 25,000 feet or the mechanical fury of a Messerschmitt's cannons. The deadliest secret was a sound, a quiet, insidious rhythm that echoed in the marrow of the machine. It was the sound of a slow, steady drip. Blink, blink, blink. March 8th, 1943, 11:34 in the morning. Inside the cavernous, metallic gut of a Boeing B-17F flying fortress, the world had shrunk to the size of a coffin. Here at Royal Air Force Station Molesworth in England, the headquarters of the 303rd Bombardment Group, 26-year-old technician James "Jimmy" Holland was hunting for that sound. A painter by trade, he was now an impromptu detective, wedged inside the No. 2 main fuel tank of aircraft 42 to 30,177. The air was thick with the intoxicating, headache-inducing vapor of 100-octane aviation gas. It coated his tongue, stung his eyes, and felt like a physical weight in his lungs. In one hand, he held a government-issue flashlight, its beam cutting a weak, jaundiced cone through the fumes. In the other, a notepad and a grease pencil. He was counting the bomber's heartbeats. Plink! Leak number 1, he muttered, his voice muffled and flat in the confined space. His light found the source, a rivet seam between sections 4 and 5 of the tank. A tiny, glistening bead of gasoline would form, swell, and then release, falling with a soft tick onto the aluminum floor. He timed it with his watch. Approximately 12 drops per minute. He scribbled it down, the pencil scratching loudly in the stillness. He shifted, his coveralls scraping against the cold, curved walls. His light swept across the tank's interior architecture, a complex maze of baffles and structural stringers designed to keep the fuel from sloshing violently during flight. The beam landed on a weld joint on an internal baffle. It was weeping. Plink, plink. Leak number 2. 8 drops per minute. He found another, then another. A structural reinforcement rivet on the upper spar was the worst so far. 15 drops a minute. A grommet where an electrical cable pierced the tank's bulkhead was practically a faucet, gushing 20 drops every 60 seconds. In this one tank, just one of 9 spread throughout the bomber's wings and fuselage, Holland counted 11 distinct leaks. He did the math right there on his notepad, the numbers seeming to swim in the dizzying fumes. This B-17F held a total of 2,780 gallons of fuel. If every tank had a similar average number of leaks, this single aircraft was losing fuel at a rate of 1.65 gallons every hour. That wasn't from the 4 massive Wright Cyclone engines gulping it down. That was just from passive, incessant dripping, lost before it ever had a chance to be burned. On a typical 8-hour bombing run deep into the industrial heart of Germany, this flying fortress would hemorrhage nearly 18 gallons of fuel into its own structure. 18 gallons. It doesn't sound like a catastrophic amount, not when you start with nearly 3,000. But Holland knew what the flight crews knew. The razor-thin margin between returning to the green fields of England and ditching in the frigid, unforgiving waters of the English Channel was often less than 15 gallons. This quiet, rhythmic dripping was the sound of men running out of time. But the problem wasn't just the quantity of fuel lost. It was where that fuel was going. It wasn't vanishing into thin air. It was seeping into the structural compartments of the wings, pooling in the dark spaces between spars and ribs. It was dripping onto hot electrical wiring, its vapor building up into an invisible, explosive cloud near the superhot engine nacelles. Every single B-17 rolling off the Boeing assembly line was, in effect, a flying bomb, waiting not for a German shell, but for a random spark. The irony was agonizing. The B-17 was designed with so-called self-sealing fuel tanks. It was a brilliant piece of engineering, a sandwich of vulcanized rubber and coated fabric. When a bullet or a piece of shrapnel punctured the tank, the fuel would instantly react with the raw rubber, causing it to swell and plug the hole. The system worked perfectly for combat damage, but it did absolutely nothing for the microscopic imperfections of its construction. It couldn't stop the insidious seeping from rivet seams, the slow weeps from weld joints, or the steady drips from cable penetrations. And those leaks were killing crews just as surely as the Luftwaffe. Between January and March of 1943 alone, the 303rd Bomb Group had lost 14 B-17s to non-combat causes. Of those 14, a staggering 9 were attributed directly or indirectly to fuel leaks. There were sudden, inexplicable fires that turned wings into infernos. Engines that sputtered and died from fuel starvation as tanks emptied far faster than the gauges indicated. And the most heartbreaking of all, forced landings and ditchings, crews surviving the flak over Bremen only to run out of gas 10 miles from home. The top brass was aware of the problem. Boeing itself had dispatched its best and brightest engineers to England to investigate. Their findings were compiled in a dense, jargon-filled document, Technical Report BT 443A, dated February 24, 1943. The report was clinical and detached. The fuel tanks of the B-17F are constructed via the assembly of 2024 T3 aluminum sections, joined by aluminum rivets and spot welding, it read. The nature of this assembly inevitably creates microscopic gaps between contact surfaces due to manufacturing tolerances, deformation from structural stress during flight, and differential thermal expansion. These leaks are inherent to the riveted construction design and cannot be eliminated by current sealing methods without a complete redesign of the fuel tank. Inherent to the design. The words echoed with a chilling finality. The verdict from the high priests of aviation engineering was clear. The leaks were unavoidable. The proposed solution? Live with it. Or redesign the entire aircraft. Redesigning the B-17 would take 18 to 24 months. It would mean halting the production lines at the precise moment the 8th Air Force was losing bombers faster than they could be replaced. Stopping production was not an option. It was strategically unthinkable. So, the official order came down from on high. Continue operations. Accept the leaks as an inherent risk of flight. Instruct the crews on emergency procedures for in-flight fuel fires. In other words, teach them how to die a little more slowly. Jimmy Holland read Technical Report BT 443 in the dim light of the maintenance hangar, the roar of departing bombers rattling the corrugated steel walls. He wasn't an engineer. He had no degree from Caltech or MIT. His official job was to spray the bomber's aluminum skin with standard-issue olive drab over neutral gray camouflage. But as he read the engineer's conclusion, a slow burn of defiance started in his gut. The report said the leaks couldn't be eliminated with current sealing methods. Holland thought, then let's use methods that aren't current. Boeing said it was impossible. A painter was about to prove them wrong. Smash the like button if you believe in hands-on engineering. Before the war, before the draft and the olive drab coveralls, Jimmy Holland had spent 8 years of his life in the shipyards of Portsmouth, breathing in the salt air and the fumes of industrial coatings. He was a painter, yes, but a specialized one. He applied protective coatings to the inside of massive fuel and ballast tanks on naval destroyers and cruisers. And in the grimy, echoing hulls of those ships, Holland had learned something that the brilliant minds at Boeing had apparently overlooked. Naval fuel tanks, built with the same heavy-duty riveted construction, had the exact same problem as the B-17s, inevitable leaks at every seam and joint. The shipyards had solved it decades ago. They didn't try to seal each individual rivet from the outside. They went inside. They coated the entire interior surface with specialized chemical sealants, creating a continuous, seamless, flexible bladder inside the tank itself. The most effective sealant Holland had ever used was a new, almost magical substance called compound PR 1422. It was a polysulfide adhesive developed by the Products Research Corporation, designed specifically for the brutal demands of aerospace and naval applications. PR 1422 was a miracle goo. It was completely resistant to aviation fuels. It remained flexible, allowing it to expand and contract with the metal as temperatures fluctuated from freezing Arctic altitudes to sun-baked runways. It adhered to aluminum with a bond that was almost stronger than the metal itself, and it could be applied in thick layers without cracking as it cured. There was just one catch. PR-1422 was designed to be applied to the external surfaces of tank components during initial construction in a clean, controlled factory setting. It was never intended to be retrofitted to the inside of a fully assembled, operational fuel tank filled with complex baffles and structural supports. The application was the problem. Manually applying the thick, sticky sealant with a brush or roller inside the cramped, convoluted geometry of a B-17 wing tank would be a maddeningly slow process. It would take days per tank, and the coverage would almost certainly be uneven, leaving pinholes and gaps. Holland needed a way to coat every square inch of the interior, every rivet head, every seam, every weld, quickly and uniformly. And then, standing there in the hangar, the smell of grease and high-octane fuel in the air, he had an idea so simple it was radical. So obvious it was insane. What if he could turn the sealant into a sprayable liquid? What if he could thin it down just enough to be atomized by a spray gun, yet have it be thick enough to form a leak-proof barrier when it cured? What if he could paint the tanks leak-proof from the inside out? On March 10, 1943, Holland walked into the office of Captain Robert Hayes, the maintenance officer for the 303rd. Hayes was a by-the-book officer, overworked and perpetually stressed, with little patience for fanciful theories from enlisted men. Holland, nervous but determined, laid out his plan. He requested permission to experiment on 8 B-17F that had been written off after suffering irreparable combat damage. Aircraft 42 to 29,531 was a ghost sitting at the far end of the airfield. It had taken a direct flak hit to its rear fuselage during a mission over Bremen. The tail was twisted, the spine broken. It was fit only for the scrapyard, a cannibalized hulk waiting to be stripped of its usable parts. Holland asked for its fuel tanks. He wanted to use this dead bomber to save the living. Captain Hayes listened, his expression unreadable. He looked at the confident young painter, then at the official Boeing report on his desk that declared the problem inherent and unsolvable. He made a decision. "You have 72 hours, technician," Hayes said, his voice stern. "I'll give you the plane. If your method works, you'll get my full support. If it fails, you go back to painting camouflage, and you never mention fuel tanks to me again. Am I clear?" "Crystal, sir," Holland replied, a surge of adrenaline washing over him. The clock was ticking. Holland and a hand-picked volunteer went to work immediately. The first challenge was the formula. In its standard form, PR-1422 had the consistency of thick peanut butter. To spray it, Holland needed to dramatically reduce its viscosity without ruining its sealing properties. After several failed experiments, he landed on a precise recipe born of shipyard experience and pure intuition. He mixed the PR-1422 with toluene, a powerful solvent that would thin the mixture for spraying but then evaporate completely during the curing process, leaving only the pure, flexible sealant behind. Through trial and error, he found the golden ratio, 3 parts PR-1422 to 2 parts toluene. This created a slurry with the consistency of enamel paint, thin enough to spray, thick enough not to run down the walls in useless drips. But Holland added one more ingredient, a touch of pure genius that the Boeing engineers had never considered. He mixed in a measure of fine, 325 mesh aluminum powder. The powder served 2 critical functions. First, it increased the sealant's thermal conductivity, allowing it to heat up and cure far more evenly. Second, and more importantly, it helped create a powerful chemical and metallurgical bond with the aluminum walls of the tank. The final recipe was a testament to hands-on ingenuity: 3 parts sealant, 2 parts solvent, and a half part of pure metal dust. He blended the concoction with a modified electric paint mixer, its stainless steel paddle churning the gray paste into a shimmering, silver-gray liquid that smelled sharply of chemicals and purpose. Next, the application method. Holland procured a standard DeVilbiss spray gun, a workhorse tool found in any paint shop. But spraying a volatile, toluene-based mixture inside a sealed fuel tank presented a potentially fatal problem. The fumes would quickly build to an explosive concentration. A single spark from a tool, a static discharge from his coveralls, and the entire wing would detonate. Holland's solution was elegant. He rigged a powerful forced air ventilation system, using one hose to pump fresh air into the tank at a rate of 200 cubic feet per minute, while a second, wider hose simultaneously extracted the heavy, flammable vapors. Finally, the curing process. PR 1422 normally took 48 hours to fully cure at room temperature. Holland didn't have 48 hours, but he knew from manufacturer's data sheet that the sealant could also be thermally cured. If exposed to a steady temperature of 65 degrees Celsius, 149 degrees Fahrenheit, for just 4 hours, it would cure completely, forming a tough, resilient barrier. So he sourced portable infrared electric heaters, the kind used to keep mechanics warm on cold English mornings. On March 12th, at 2:17 in the afternoon, everything was ready. Holland selected the number 3 fuel tank of the derelict B-17. His earlier inspection had documented 17 distinct leaks in this tank alone. It was losing a staggering 3.1 gallons per hour when full. Suited up in a respirator mask and coveralls, with the ventilation system roaring to life, Holland climbed inside. For 43 minutes, he worked methodically, the hissing spray gun coating every surface in the shimmering, silver-gray mixture. The walls, the baffles, the rivet seams, the weld joints, everything disappeared under a uniform, 1.5 millimeter thick layer of his custom sealant. When he emerged, blinking in the daylight, he immediately installed the infrared heaters, sealed the tank's access panel, and flipped the switch. The 4-hour bake began. The fate of his crazy idea, and potentially the lives of hundreds of airmen, was now cooking inside the wing of a dead airplane. For hours and 12 minutes later, he cut the power. He waited for it to cool, his heart pounding. When he opened the panel and shone his flashlight inside, he gasped. The interior was seamless. The sealant had cured into a smooth, continuous, rubber-like liner, bonded perfectly to the aluminum. It looked like it had been manufactured that way. Now came the only test that mattered. On the morning of March 13th, 1943, under the watchful eye of a skeptical Captain Hayes, Holland and his assistant filled the treated tank with 305 gallons of 100-octane aviation fuel. Then, they pressurized it to 3 pounds per square inch, simulating the stresses of high-altitude flight. Holland grabbed his flashlight and crawled into the wing's structural compartment beneath the tank, his gaze fixed on the areas where 17 leaks had been steadily dripping just 2 days before. The rivet seam between sections 4 and 5, bone dry. The weld joint on the internal baffle, bone dry. The structural reinforcement rivet, bone dry. The electrical cable penetration, bone dry. He checked every single one of the 17 previously documented leak locations. 0. Not a drop. Not a weep. Not even a damp spot. The tank was held full and under pressure for a full 24 hours. Still nothing. The silence in the wing was absolute. The deadly drip had been silenced. Holland had done the impossible. He reported the results to Captain Hayes. The captain's response was immediate and decisive. You have authorization to modify every B-17 in this group. How many men do you need, and how long will it take? The fix that saved 3,000 lives was officially born. Holland calculated that a trained 6-man team could seal all 9 tanks of a single B-17 in about 18 working hours, spread over 3 days to allow for curing. With 34 operational B-17s in the 303rd Bomb Group, he estimated he could make the entire fleet leak-proof in 6 weeks. On March 15th, the project began. Holland's makeshift laboratory became a streamlined production line. The process was standardized, perfected, and repeated with military precision. Drain the tank. Clean it with solvent. Dry it with hot compressed air. Mix the sealant to the exact formula. Spray a uniform coat. Cure it thermally for 4 hours. Inspect, fill, and verify. By April 28, 1943, every single one of the 303RD's 34 bombers had received the Holland treatment. The results were immediate and astounding. Before the modification, the group's bombers lost an average of 17 gallons of fuel to leaks on a typical mission. After, that number plummeted to just 2.4 gallons, an 87% reduction. But the most significant impact wasn't the fuel saved. It was the elimination of the volatile fuel vapors inside the wing structures. Between May and August of 1943, a period of intense and costly bombing operations, the 303rd Bomb Group did not record a single non-combat fuel fire. Not one. Word traveled fast. Commanders from other bomb groups, plagued by the same mysterious losses, noticed the 303RD's remarkable safety record. In June of 1943, the Holland method was officially adopted by the 8th Bomber Command and authorized for implementation across the entire European theater. Between July 1943 and the end of the war in May 1945, an estimated 2,400 B-17s were modified with variations of Holland's sealant process. A post-war technical report, AFTC 5512, laid out the stunning impact in cold, hard numbers. The implementation of the internal fuel tank sealant resulted in a 76% reduction in non-combat fuel fires and a 43% reduction in forced landings due to premature fuel starvation. The report concluded with a conservative estimate. The lives of 2,800 to 3,400 American airmen were saved by the modification. That's up to 340 complete B-17 crews who returned home because a 26-year-old painter refused to believe that a problem was unsolvable. Subscribe to uncover more hidden history of World War II. But Jimmy Holland never received a medal for his innovation. His name never appeared in an official commendation. The method was classified as sensitive technical information. Admitting that the fortresses had a massive leaking problem would have been a disaster for crew morale and valuable intelligence for the enemy. Holland was quietly promoted from technician to technical sergeant in July 1943, a standard rank increase with no special mention of his world-changing fix. Boeing's engineers eventually incorporated a version of the process into the later model B-17GS, applying the sealant during assembly at the factory. But the corporation never publicly acknowledged that a low-ranking aircraft painter had single-handedly solved a problem their own experts had declared impossible. After the war, Jimmy Holland returned to Portsmouth. He went back to the shipyards, working as a quality control inspector for 32 years. He retired in 1977 and passed away in 2001 at the age of 84. His obituary in the Portsmouth Herald noted his service in World War II, but made no mention of the 2,400 bombers he had sealed or the thousands of lives he had saved. His legacy was as silent as the leak-proof tanks he had created. But it is not entirely forgotten. In the climate-controlled halls of the National Museum of the United States Air Force in Dayton, Ohio, sits a beautifully restored B-17G, serial number 44 to 83,624. Its original fuel tanks are still sealed with the Holland method. During its restoration in 1998, a curator inspected those tanks. 53 years after the sealant had been sprayed on in a cold English hangar, it was still there, still intact, still flexible, still perfectly bonded to the aluminum. The curator documented the finding with a simple, powerful note. The sealant applied using the Holland technique in 1944 shows zero degradation after 5 decades. The longevity of the material and the integrity of the application are extraordinary. This is a testament to both the quality of the work and the efficacy of the method developed. Sometimes the greatest solutions to the most complex engineering problems don't come from corporate laboratories or men with doctorates. They come from the hands and minds of technicians on the ground, the people who refuse to accept that something is inherent to the design when lives are on the line. That is the lesson Jimmy Holland taught the world from inside the wing of a bomber in 1943. It was a lesson that 3,400 men who came home to their families never needed to have explained. They lived it. They flew in bombers sealed by a painter who decided